Hi everyone. Okay, so we have for today the notes for lecture 15. The top of my page it says lecture 16, but I crossed it out. But if you download the blank notes, then you'll see lecture 15 in yours. So today we're going to start to talk about Newton's method in the context of multivariate functions. So we'll just have a refresher on multivariable calculus, and then just show that Newton's method works the same way for multivariable functions as it does for scalar value functions. But just in case we want to have a big refresher on multivariable calculus in case you have forgotten how some of this works. Okay, so let's just start with this first definition here. So if I have a function of n variables, f, that I'm just going to define the partial derivative with respect to one of those variables xi at a point as the derivative of that function with respect to xi evaluated at that point, and then just plugging in for all the other functional values of the other variables, x1, x2, onto xn except for xi. And so we'll use a more compact notation, either the partial of f with respect to xi, or f with a little xi, or dif, where the I is the index of the variable with which you're taking the derivative with respect to. So the gradient of f, written with this upside down triangle, is a vector, where each element of the vector is the partial derivative of the function with respect to each of the variables. So if you have n variables, this is an n-dimensional vector valued function. So let's just do an example here to remember how to compute the gradient and evaluate it at a point. Move it over here. Okay. So I have f of x, which is a function of four different variables, x1 to x4. So we'll do the partial. So partial of f with respect to x1. Let me make sure it's big enough for you to see. Okay. X1, well, actually everything appears in the sign, so it's always going to have to be a chain rule, right? Sine becomes cosine with the same argument. So x1 squared plus x1, x2 minus x3 squared times x4, and then times the derivative of the argument of the cosine with respect to x1, which is just 2x1 plus x2. Same for f with respect to x2. Well, let me turn off this big light. Get rid of that hand shadow. Okay. So same cosine, x1 squared, x1, x2 minus x3 squared, x4. The derivative with respect to x2 is just x1. Partial of f with respect to x3, same cosine again. And the partial with respect to x3 is just 2x3, x4. And the partial of f with respect to x4, which is the same cosine, x1 squared, x1, x2, minus x3 squared, x4, and the derivative of the argument with respect to x4 is just minus, oh, excuse me, there should have been a minus in the previous one here, minus x2, and it should be minus x3 squared. Cool, and I want to evaluate it at this vector A. So the partial of f at A. So when I plug in A for the cosine, let's just make a little bit of side work. It's the cosine of 1 squared plus 1 times 1 minus x3 squared, which is just 1 times 2. So it's 2 minus 2. So it's cosine of 0, which is 1. So the first element is just going to be 1 times 2x1 plus x2, which is 3. And the next element will be 1 times 1, 1 times minus 2 times minus 1, which is 2 times 2, so 4. And then 1 times minus 1 squared, which is positive 1, minus 1. So here is our gradient of a vector valued function at a point. Excellent. Okay. What about second derivatives? Make sure you can see that. Okay, so our next definition is for the second order partials. So the second order partials are just the first order partials taken in the right order, right? So if I do the partial with respect to xj, xi, I have to do the partial with respect to xi, the right more one first, and then xj. And I can also write it as xi, then xj in the subscripts. So let's do an example here and make sure we remember how to calculate these partial derivatives for this function of two variables. So I think the easiest way is let's calculate the two first partials first. So the derivative with respect to x1 is just cosine x2 plus x2 e to the x1. That doesn't change. And the partial with respect to x2, cosine becomes a minus sign, so minus x1 sine of x2 plus e to the x1. So the second partials, f, I'll do it with the partial sign, f of x1 squared. So I need to take the derivative of fx1 with respect to x1 again. This cosine of x2 goes to 0. It's a constant. I'm just left with x2 e to the x1. The second partial of f with respect to x2 2 times will just be fx2 with respect to x2 again. So in this case, the second summand doesn't have an x2, so that becomes 0. So all I'm left with is the derivative of the first term, which becomes minus x1 cosine x2. The first, mixed partial, x1, x2, we know from the notation above, we have to take fx2 and now take the derivative with respect to x1. So this is minus sine x2 plus e to the x1. And finally, the second partial that's mixed with respect to x1 and then x2. So I take fx1 and now the derivative with respect to x2. Cosine becomes a minus sine x2. And x2 e to the x1 is just e to the x1 because it's constant, or it's linear in x2. Awesome. So that's probably very familiar. And the thing to note is that the mixed second partials are equal. We have a theorem about that supports why this is the case. So we have theorem 1, this equality of mixed partials, and it says that if f is a function of n variables and that f and all of its first derivatives and all of its second derivatives exist in an open set at a point, around a point, and they're all continuous at that point, then it doesn't matter which order you do the second derivatives in. The mixed partial should be equal. And so if I look at this function, this is trig functions, exponential functions, all of this stuff is continuous. So I have no worries. And the theorem 1 applies. That supports the equality of the second partials. Okay, let's remember a matrix that allows us to group second partials of a vector valued function. So on page 3 of the notes, we have the next definition, which is for the Hessian of a function f. So if I have a function of n variables, the Hessian is going to be this matrix where the ijth entry is the second order partial with respect to first xi and then xj. And so with xi and then xj, if I think of it in the bottom, but then I guess the order of it is actually flipped, right? I would do, for example, the 1, 2 entry would be the partial with respect to x2 and then x1. I can write it here with the partial signs or our shorthand, or I can actually look at the columns of this and notice that this is the derivative with respect to x1 of the gradient of f. So if I take the x1 partial derivatives first and then the gradient of that, I can get the first column and the partial with respect to x2 and then the gradient of that and so on. I get the n columns of this matrix. So this is an n by n matrix. And so if we can say that f and its derivatives are continuous in this open set around a point, then, or I mean, for the function we saw it was everywhere, then we can show, or we can assume that the Hessian itself is symmetric, right? Because these partials should be the same, these partials should be the same, and so on. Okay, let's think of a way that we can use this to do a linear approximation in line with what we do with the Taylor expansion for a scalar valued function. So if I had a function of n variables, this linear approximation for a vector valued function would look really the same as it would for a scalar valued function. You know, for a scalar valued function, if I said, a lot of times I write it as x plus epsilon. It looks a lot like, or is approximated by, f at x plus f prime at x times epsilon, this kind of thing. So for a vector valued function, we have f at a plus h, some perturbation. This is a small perturbation, is approximately f at a plus the gradient of f dotted with h, the h vector. I can also do what we would call a second order or a quadratic approximation. This is now, instead of having just the first, up until the first two terms of the Taylor expansion, this is the first three terms up until the quadratic term of the Taylor expansion. And so we get something like an h squared. So when I want to write it in terms of vectors and matrices, now f of a plus h is approximately f at a plus the gradient of f at a dotted with h plus 1/2 h transpose times the Hessian at a times h. If I think about the dimensions here, how this should work out, these should all be scalars, right? Because this is going to be, it's a scalar valued function of multiple variables, right? F is a scalar valued function, but it has a bunch of inputs. And so this is a scalar, this is a scalar, the gradient dotted with a vector, the dot product is always a scalar, and this is 1 by n times n by n times n by 1. So a scalar here as well. So let's use this idea of a linear approximation to think about how to approximate just like some numbers raised to certain powers that may be kind of difficult to compute if I wanted to do it directly, right? So these numbers, let me move this up so we can see the workspace here. So I want to look at 2.9 cubed plus 0.1 squared. So it looks a little like a little like 3 cubed, right? Because 2.9 is kind of like 3 plus 0 squared, because 0.1 is kind of like 0. And so I want to think about this in terms of the notation that we've used previously. I'll think of f, a function of x1 and x2, as being x1 cubed plus x2 squared, where a, the point I want to approximate around, is what this looks like. It's kind of like 3, 0. And h is like this small perturbation. So it's the difference between 3 and 2.9 is minus 0.1 for the first element, and 0 and 0.1 is plus 0.1 for the second element. I hope that that makes sense. Because in that case, if I want to know what is the functional value of 2.9 and 0.1, this is f of, I could say this is a plus h, right? This is 3, 0 plus minus 0.1 times 0.1. And I know from linear approximation that this is like f at 3, 0 plus the gradient of f at 3, 0 dotted with h minus 0.1, 0.1. I hope that that makes sense there. Okay, so let's compute the gradient of f. And so what the instructions actually say is, let's do this for a linear and a quadratic approximation, and then we'll compare it to the exact value, which is approximately 24.399, and we'll see which one is better. We think, quadratic approximation should be better, but let's check it out. Okay, so the gradient of f, the derivative with respect to x1 is 3x1 squared. The derivative with respect to x2 is 2x2. Awesome. And so this guy becomes, this is like some side work I'll put in a box. So this becomes 3 cubed plus 0. So 27 plus 0 plus the gradient at 3, 0. So that's going to be 3 cubed and 0 again, right? So 27 and 0 times minus 0.1, 0.1, which is 27 plus negative, this divided by 10, 2.7, right? Which is 24.3. That's the linear approximation. Make sure you can see that. Okay, so that is the linear approximation. Let's look at the quadratic approximation. So for that, we need to compute the Hessian. Oh, sorry, lost my place. Okay, here we go. So the Hessian, so the first thing I guess to notice is that for the quadratic approximation, our actual value here is going to be approximately whatever the linear value was, 24.3, plus this higher order correction, which is 1/2 H transpose, which is minus 0.1, 0.1, times the Hessian, whatever that is, I'll just write a matrix and we'll fill it in, times H again, minus 0.1 and 0.1. Okay, so what's the Hessian going to be? Let's do it as a little side work here. So we want to take, this is the partial with respect to x1, the partial with respect to x2. Let me see if you can see it right. Okay, so I want to take the partial here with respect to x1 again. So 6x1 with respect to x2 at 0. Likewise, the second term with respect to x1 is 0, and then 2. Whoops, 2. Okay, so the Hessian at the point we're looking, 3, 0, should be 18, 0, 0, 2. Cool. So we can multiply this all out. And what do we get? We have this as 24.3 0.3 plus 1/2 minus 0.1. 0.1 times minus 1.8, 0.2, which is 24.3 plus 1/2. The two minuses become 0.18 plus 0.02. And that actually becomes 24.4. 24.4, really small correction. And so doing a linear approximation, so I'll put a box around here, this is the quadratic, is not a bad approximation of the actual value here, but doing a quadratic approximation makes it better, makes it closer. Okay, great. Oh, whoops, excuse me. I forgot that I left more room on the next page of notes for that example, so it didn't get very crowded. Okay, so I guess you'll see that if you go through on your notes. There's all this room here. So let's talk about a couple more definitions so that we can relate these calculus quantities to the behavior of a function locally. Okay, so we have a definition. So we have a scalar valued multivariate function, f, and we say that f has a local maximum at a if f at a is bigger than all of the f of x's for points in some neighborhood of a. So this would be like some open set of a, and a minimum if f at a is less than all the local points. So how would I test that? Is that I can use this first derivative test. Now, this test is necessary but not sufficient. So let's look at what the test says. It says if I have a local max or min at a, then the derivative, in this case the gradient, is 0 because it's a multivariate function. So the idea is that a is called a critical point if this is 0. So this is equivalent to saying a is a critical point of f, but not every critical point has to be a local max or min. If I think of a scalar valued function, it's just like a function that, for example, went like, it has a 0 deriv at some point here, but it's not a local max or min, right? So, yeah, and looking for local maxes and mins, this can be the kind of thing that we look for, and the kind of test that we can do using calculus. Let's look at another definition that takes care of this case if it's not a max or a min. So if A is a critical point in the interior of the domain of f of a, so not on the ends of if we have some domain for the function, because then the idea of like a nearbyness of a neighborhood, you know, when we write neighborhood, it's kind of loose, but what we would mean in more rigorous mathematics is an open set, and we can't define that in the boundary of a domain. So let's say we're in the interior of a domain, so we have an open set around this point A, then f has a saddle point at a if every neighborhood of a has some points that are greater than f of a and some points that are less than f of a. So it's a critical point, but it's not a max or a min. So how can I relate this, or can I relate this to these calculus quantities? So we've said I can relate the idea of a critical point to the gradient, but maybe I can also relate this back to this matrix like the Hessian to do a multivariate analog to the idea of like the second derivative test. I don't know if you remember from calculus, you probably do. You want to find if something is a max or a min, you do the first derivative test to see if it's a critical point, and then you classify if it's a max or a min by finding the second derivative. And if the second derivative is positive, then it's concave up, and so the function has a minimum. If it's negative, it's concave down, so the function has a max. And if it's 0, that's this idea of a saddle. You can't say anything. So we're going to try and build that idea here into the multivariate sense. So let's remember a little bit about matrices. Let's just consider an n by n matrix A that is symmetric, and I can write some function f of x in this quadratic form. So it's x transpose ax. So f of x is a scalar valued multivariate function. Now we have to assume that a is invertible so that all the or equivalently all the eigenvalues are non-zero. So if we have this, then we have these different ways that we can classify A. So we call A positive definite if x transpose AX is greater than 0 for all x that are non-zero. It's negative definite if that quantity x transpose AX is negative for all of the x's that are not 0. And we can't say anything. It is indefinite if we have some x's that are greater than 0 and some x's that are less than 0. So these are the definitions of positive definiteness, but it's kind of hard to test with the definition because you have to test every x. So we could actually appeal to the eigenvalues and the eigenstructure of A to be able to find positive or negative definiteness of a matrix. So first, let's just recall that if A is symmetric, remember we're doing this with Hessians, probably with pretty well-behaved functions which are continuous. So that's why we really care about symmetric matrices, because the Hessians we're going to look at are probably symmetric. So if we have a symmetric matrix, all the eigenvalues are real. So we're probably just going to talk about real numbers here. So here's our next theorem to actually determine if a matrix is positive or negative definite. So let's let A be an n by n matrix that's symmetric and no 0 eigenvalues. Then this matrix is positive definite if all of the eigenvalues are positive, negative definite if all of the eigenvalues are negative, and indefinite, we can't say, if some of the eigenvalues are positive and some of the eigenvalues are negative. So that's how you actually compute whether or not a matrix is positive or negative definite. You just look at the signs of all of the eigenvalues of all of the spectrum. So let's just practice finding whether or not a matrix is positive definite or not, positive, negative definite, or indefinite, and then we'll relate this back to a multivariate version of the second derivative test for finding maxima and minima of these functions. Okay, so here's two matrices, and I want to know if they're positive or negative definite. So let's find the spectrum. So for A, lambda I minus A, the determinant is going to be lambda minus 5, 2, 2, lambda minus 5. So lambda squared minus 10 lambda plus 25 minus 4. So lambda squared minus 10 lambda plus 21. Oh, yeah, 7 and 3. Okay, so lambda minus 7, lambda minus 3 equals 0 implies that the spectrum, the eigenvalues are 7 and 3, which are both positive, which implies that A is positive definite. Well, it's the same thing for B. Lambda I minus B. So lambda minus 1, 4, 4, lambda plus 5 is going to give me lambda squared plus 4 lambda minus 5 and then minus 16. So lambda squared plus 4 lambda minus 21. Oops, which I then can factor as lambda plus 7 lambda minus 3 and set that equal to 0. Is that right? That looks good. Okay. So lambda now is 3 and minus 7, which are different signs, which implies that B is indefinite. Okay, so now we're going to move on to talk about the second derivative test. But actually, I'm just going to stop this video here so the videos don't all get too huge, and I'll start on the next video here. Just a moment.